So we've proven two of the Sylow theorems, and we've proven one of the Sylow theorems. Let's prove the other two. So let's go to the second one, and let's prove it. So here we want every p group is contained in a Sylow p subgroup, and any two Sylow p subgroups are conjugate. So let H and G be a p group, or a p subgroup, I'll say, because it's a subgroup. Remember, G has size p to the r times m, where p does not divide m. Okay? So let P be, let's see here, so this is going to be a subgroup of R, this is going to be a Sylow P subgroup. So of course, to prove this one, we need this one. Well, at least this proof relies on part A, because we can't define such a P if we don't know that Sylow P subgroups exist. So anyways, let H act on G mod P, which we are going to define to be X, by H acting on GP is just going to be HGP. You should be able to see from this that this is going to be a group action, but you can check it more in more detail if you want. Also, one thing to keep in mind is that X, G mod P, when we were talking about modding out by subgroups, this is always going to be a set. We can define the set by modding out by P. This isn't necessarily going to be this is not necessarily going to be a group. Particularly if P is not normal in G, then this is not a group. It's just a set. And there are plenty of examples of Sylow P subgroups which are not normal. But anyway, so that's something to keep in mind. X is just a set, but that's fine because we're taking a group acting on a set. And so we don't need this to be a group. But just to keep in mind. Anyways, so since x to the h is going to be less than or equal to the size of x, which is going to be finite, and so we can apply the first lemma that we discussed when we were talking about p groups way back last video or the video before. I think it was the video before. So anyways, what we know is that not x to the h here. Here it's just x, but the size of x is going to be equal to the size of x to the h mod, okay, well this is not an equal, but an equivalent. This is mod p. Remember, for this to hold, we needed wait a minute, what did we need for this to happen? Right, because we have a p group acting on a set. And H is a p group, and so this works, okay? So what is the size of x? Size of x equals p to the rm, because it's g mod p, and so it's the order of g divided by the order of p. The order of g is p to the rm, the order of p is p to the r, and this is just m, which certainly is not equivalent to 0 mod p, because if it were, then p would not divide m. P would divide m if this were the case, if it were equivalent to 0 mod p. So anyways, so what this means is, so if this is not equivalent to 0 mod p, then this cannot be 0. So the size of x to the h is not equal to 0, which means that x to the h is not equal to the empty set. Remember, when we wrote this down, there was nothing preventing that from happening. Just because we defined the set certainly if this is the empty set, then its size is going to be finite, and so that's okay, and this can still make sense. But in this case, it's not true that x to the h is empty. We had to prove this. Okay? So since it's not empty, let's pick an element in there. And let's call it GP. This is going to be an x to the h. Remember, this is just an element of x, and this is what elements of x look like. Just quotients. Okay? So now for all h in h, we know that hg p is equal to gp, because that's what it means to be an x to the h. It means that every element of h fixes this under the action. And so, let's see here. So, since hgp equals gp, we know that well, technically, I guess this would be g inverse hp. G inverse hgp, so this implies that g inverse hgp is equal to p, or in other words, g inverse hg is in p. So h is contained in gp g inverse, because this holds for every single h in big H, and so g inverse capital HG is contained in p, and just multiplying on the left and right gives h is contained in g times p times g inverse. Okay? Now, note that GP1G inverse, just in case this isn't like something that's immediately obvious, if these two are equal, if GP1G inverse equals GP2G inverse, and multiplying on the left and right, on the left by G inverse and on the right by G gives you P1 equals P2. So if you consider the map that sends an element little p of capital P to G little p G inverse, this shows us that it's going to be an injective map, and so certainly every element is going to be mapped somewhere, and so what that tells us is that the size of P is equal to the size of G PG inverse. Hence, H is contained in the Sylow p-subgroup GPG inverse. And so there we go. So there is indeed a Sylow p-subgroup such that H is contained in there. And now from here, okay, so that's the first part. Now we want to prove that any two Sylow p-subgroups are conjugate. So for the next part, if H is a Sylow p-subgroup, then H is contained in GP G inverse by the previous result. So if H is contained in GP G inverse, and the size of H is equal to P to the R because it's a Sylow p subgroup, and the size of this is equal to P to the R because it's also a Sylow p subgroup, then they have to be equal. So H is GP G inverse. And clearly, this is going to hold for every single, this is going to hold for any two Sylow p subgroups, and therefore, we have any two Sylow p subgroups are conjugate. And so that's the proof of B. And that also kind of shows us why we group these two statements together because the second statement follows from the first almost immediately. Although in order to see that, you have to consider this, although I guess you can sort of see from the statement that it's not much, because you just say, oh, well, if you have a p-Sylow subgroup, then in particular it's a p-group, so you use this fact, and then it's almost immediate. So that's why we were to combine those two together. And let's see here, that took me about 10 minutes. And each video, once I get to about 21 minutes in, my phone does this thing where it breaks up the video into two different videos. Then I have to go in and kind of splice them together, and it's all messy. So I really try to avoid making videos greater than 21 minutes long. But given that we did the second Sylow piece theorem in less than 10 minutes, or just about 10 minutes, now let's prove Sylow theorem with a vengeance. So we want to prove these two statements, and let's see here. So what we're going to start with is we're going to let S, script S, be the collection of Sylow p subgroups of G. So let P be an element of script S. We know that script S is not empty because of part A. So let P act on script S by conjugation, i.e., if we have P and Q in script S, then P acting on Q is equal to PQP inverse. And so here, this multiplication is the group action, and these multiplications are multiplication in the group. Okay? Let's see here. Since P is a P group or a P subgroup, whatever you want to call it, the size of script S must be equivalent to the size of script S to the P mod P. So here this is lowercase p, this is capital P, this capital P that we fixed. Okay? So let's see here. So now what we want to do is we want to use this statement to get this statement. Clearly the size of script S is NP by definition. So what we want to prove is S to the P is that this norm is 1. We want to prove that there's only one thing in here. Okay, so let Q be in S to the P. Here, I had to write this out. So for all, we'll call it X in P, QX Q inverse equals Q. That's because that's what it means to be an SP. That means that if you take anything in P, this action is going to fix Q. Okay, so now let NQ be the normalizer of Q, which is really just the stabilizer of Q under this action. So this is GQ G inverse is equal to capital Q. So then P and Q are two Sylow p subgroups of NQ. And why is that? That's because certainly they're both groups of size P the R. If you just look at the set, well, if you have anything in Q, then that times Q, then like little q times big Q times little q inverse is obviously you're multiplying three things in Q together. So that's going to be contained in Q. And of course, GQ G inverse is going to have the same size as Q, and so therefore you have containment both directions, and so it works out. And then the other thing, obviously, P is going to be in here because if you take anything in P, then you know that for all x in P, x, Q, x inverse equals Q. And so we know from the fact that Q is in S to the P that Q is a subgroup of NQ. Okay, and so then we have two Sylow subgroups of this. So by part B, P and Q are conjugate, but they're not just conjugate in G here, they're conjugate in NQ, i.e. there exists an X in NQ such that P is equal to XQX inverse, because that's what it means to be conjugate in NQ, which is more specific than being conjugate in G. But look, this is in NQ, and so XQX inverse is going to be equal to Q. And so Q is equal to P. This holds for all Q in SP. So that means that S to the P contains just the element P, because everything in S to the P is just P. Okay, so then script S equals script S to the P mod P becomes, and because remember we said script S, the norm of this is just the number of Sylow P subgroups, which is what NP is defined to be. And so this is equal to, well, S to the P has just one thing in it, and so its size is 1. 1 mod P. Okay, so we're almost done. All we have to do is that last thing here, and that turns out to be pretty quick. So we're going to let G act on script S by conjugation, rather than just letting P act on S by conjugation. Okay, so NP divides, no. So now NP, the number of P Sylow subgroups, this is just equal to the orbit of P under G, because we know that all Sylow P subgroups are conjugate, and so if we consider the set of all possible things that we get by conjugating P, we're going to get all Sylow P subgroups. And so they're all going to be contained in this orbit here, and so the size of that is equal to NP. Okay, well this is an orbit, so let's think, orbit stabilizer. So this is equal to, the orbit stabilizer, so the size of G is equal to the orbit under an element X times the stabilizer under the element X. So this is equal to the size of G under the stabilizer in G of P, right? Yeah. And in fact, this stabilizer is just the normalizer, it turns out. The normalizer of P. Wait, let's see here. This normalizer, maybe this should have been G and P. Let me just check here real quick. Nope. That's fine. Yeah, we're just defining this set here, anyways. So I don't think that this is necessarily the normalizer or the stabilizer under this action. Like I said earlier, we're just defining this as a set. I think this is just the stabilizer of Q under this action, which is not the same as this action. But anyways, this is all. I never stated anything like that. I just said let NQ be this, and so this is all valid. Anyways, so this is this divided by this, and so certainly this is going to divide the order of G, which is P to the R M. And NP is equivalent to 1 mod P. Well, if it's equivalent to 1 mod p, if NP is equivalent to 1 mod p, then it can't divide p to the r. Because if it divided p to the r, then it would be it'd be equivalent to 0 mod p, which is not 1 mod p. Okay, so if NP divides p to the rm and it doesn't divide p to the r, then it must divide m. And there we go. That's the last result that we wanted to prove, and therefore we have proven the Sylow theorems.